Hello, ELT132. This is Roger Young, and this video discusses the initial part in designing a synchronous counter. Okay, so as you can see, we have the classical design technique right up here on top, right? So the first step is obviously you define the problem. Remember, we're defining it, we're going to go through and end up with a circuit. Previously, you were given a circuit and went all the way back and you you developed a state table and you ended up with a state diagram, right? So now we've turned it around, so you know the counter you want to build, and this is how you're going to build it, right? So first, you define the problem, all right? Before you can begin the design of the circuit, you have to know its purpose, what its purpose is, and what it should do under all possible conditions. So, I've listed here the first item. Again, this comes from the text. It's define the problem. And the example they have in the text is the circuit that you're going to build. It must count from in binary from 0000 to 1101. I'm saying these numbers from the least significant bit to the most significant bit, right to left, and repeat. All right, that's very important because then you know how it's supposed to count, but you also have to know how it's supposed to progress, right? The output progresses by 1 for each applied clock pulse. The outputs are 4-bit numbers, so we require 4 flip-flops. All right? So in the lab, you're going to have to do this, but this is the first step, and it's so critical you define it right. Think about it. It's like building a house. If you don't have a good foundation and the drawings aren't right, then the final product's not going to be pleasing to the customer, right? So after you've defined the problem, the next thing you do is, if you look over here on the right, you're going to have to draw a state diagram. And notice, we start at 0, 0, then we have an arrow pointing to the next state, 1, 0, 0, 0, pointing to the next state, 0, 1, 0, 0, then another arrow pointing to the next state, 1, 1, 0, 0. And you can see it progresses all the way around here. This is the counter that you defined. Finally, the last state is 1, 1, 0, 1, and then it repeats or recycles back to the beginning and just repeats itself, right? So that's the second step right here. You need to draw a state diagram. They say pictures are worth 1,000 words. Well, it's definitely true here, right? Now, the next step is you need to make a state table. This is number 3. Make a state table showing each present state and corresponding next state. So if you look over here in table 9.9, don't worry about these inputs right here. We're just looking at the present state and the next state. The present state starts at 0, 0, 0, 0, and the next state is 1, 0, 0, 0. So obviously we're going to take this state, that becomes the present state now, and from this state, 1, 0, 0, 0, the next state after that is going to be 0, 1, 0, 0. And obviously now that next state becomes the present state, and you progress all the way through, right? Notice here at the bottom, right, it's 1, 1, 0, 1. I shouldn't say at the bottom. This is the last step in the counter. 1, 1, 0, 1, and it progresses to 0, 0, 0, 0. In other words, this is when it repeats, right? That's an important piece to keep your eyes on. Also, note these 4 pieces here at the bottom, these 4 states. Those are unused states, aren't they? I mean, they aren't used in the counter. And the next state are all X's. In other words, we really don't care where they go in this example because they're not used. So notice these are all X's. With this state table, you must fill in everything. So these areas right here, these 3 blocks I just went over, those are used, obviously, for the counting, right? It starts from 0, ends at 11, right? But the rest of these, the rest of these states, the 4 additional states here, these, the next state, it does not matter, and the JK values at for these states are use the X, which means the I don't care state. All right. We aren't really even looking over here yet, but I just wanted to tell you about that. So those are the interesting things to keep your eye on when you're drawing your state table, right? Now we're going to look at the JK portions here, right? Because each one of these outputs corresponds to a flip-flop. So since we have 4 outputs, 4 Q outputs, we are going to have 4 flip-flops, right? Now, the prior video, we talked about the excitation table. And since we're using a JK flip-flop, I listed the JK excitation table down here. Now let's just read what step 4 is. Use the flip-flop excitation table to fill in the JK entries in the state table. All right? So let's look at this one, for example. We're going from a 0, we're at Q0, right? If Q0 is 0, we want to go to a 1. All right? So let's all look down our transition table. All right, we want to go from a 0 to a 1. So J and K is a 1x. So we're going to come over here to the J0, K0, and it's a 1x. Got it? Now, how about the rest of them? We're going from a 0 to a 0, right? 0 to a 0. Q1 starts at 0, Q1 ends at 0. So this is a 0 to 0. So all these others are 0x. Hence we fill in 0x, 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 right? And remember, each one of these JK pairs refers to the flip-flop. This one here on the left refers to the most significant bit. I'm going to call it flip-flop 3. Then we have J2K2, which is flip-flop 2. We have J1K1, which is flip-flop 1, and J0K0, which is flip-flop 0. And that's obviously your least significant bit. J3K3 are your most significant bit. So let's just do one more line for an example for you. So the next state ended up on this level as 1, 0, 0, 0. So let's take that down and copy it here, right? So if we're at 1, 0, 0, 0, if you look up here, we're at 1, 0, 0 in your state diagram, the next one is 0, 1, 0, 0. Well, we're just going to put that in right here, right? Because that's the next step. That's the next state. Well, then we just have to go through each one of these, right? Let's start at the least significant bit. Least significant bit, you're going from a 1 to a 0, right? Well, if we're going from a 1 to a 0, let's look at our state table. We have to have x1. So if we come all the way over here to J0, K0, it's x1. Get it? x1. Now, let's look at the next one. Q1 is going from a 0 to a 1. Well, let's look at our state table. 0 to a 1 is going to be 1x, correct? So if we come all the way over here to our flip-flop 1, there we are. J1K1 is a 1x. Get it? Now, how about Q2? Q2 starts at 0 and ends at 0. The next state is 0. So it's going from a 0 to a 0. Let's go to our transition table. A 0 to a 0 transition is 0x. So we'll look at flip-flop number 2. Flip-flop number 2 here is a 0x. And finally, let's look at flip-flop 3. We're starting at 0. We're transitioning to a 0, so it's going from 0 to 0. A 0 to 0 transition is 0x. Hence, you'll see we have it for flip-flop 3, for this transition, J is 0 and the K is x, so it's 0x. and you follow this method we just talked about to fill in the entire table. Now look, some people may think they can remember these transitions off the top of their head, but it's always useful to have a transition table filled out next to you when you're doing this by hand, because it's very easy to make a mistake. And all you have to do is make one mistake in here, just one X in the wrong place or 0 in the wrong place, and it's going to completely make your circuit so it doesn't work. So I would strongly recommend that when you do these problems, you have a transition table right next to you so you can use it when doing your state table. All right, I hope you've learned something out of this, and the next series we're going to learn about what to do with this state table to generate your circuit. Thanks for watching.